Good evening, everybody, and welcome to Winchester Cafe Sci Online, and a special welcome to those joining us for the first time. It's still uncertain when it would be sensible to resume live meetings, so we're scheduling online events at least until the end of 2021. Accordingly, we've just renewed the annual Zoom subscription, and if you'd like to contribute, you may do so at paypal.me/wincafesci, which is on the screen behind me, and I'll pop it into the chat as well. Apologies for the broken link in the email. People tried to contribute there and had problems. A recording of this talk will be posted on our YouTube channel, where you'll find recordings of all our online talks. I'll put details of that in the chat too. You can also find the links on our website, wincafesci.org.uk. If you enjoyed tonight's talk and you're not on our mailing list, you can sign up for it on our website to be notified about future talks. After tonight's talk, we'll take a break for a few minutes before the Q&A. Please put your questions into the chat and I will read them out. That includes our viewers on YouTube. Tonight's speaker is a professor of structural biology focused on the global challenge of plastic pollution and leads a team of scientists researching natural enzyme discovery and engineering. Their work revealed the detailed workings of an enzyme that can digest PET, and more recently demonstrated that engineering these enzymes can increase the speed of breakdown. Found in single-use drink bottles, packaging, clothing and carpets, PET can take centuries to decompose, and together with other plastics is accumulating in our environment at a staggering rate. A biological catalyst that can break PET down into its original building blocks opens new opportunities for recycling towards a circular plastics economy. Their work on PET digesting enzymes has been widely covered in the media, following two key papers in 2018 and 2020 in the journal PNAS, and the project received the Times Higher Education STEM Research Project of the Year in 2019. The group is rapidly expanding due to a £6 million grant from Research England, which has allowed the recruitment of 15 additional researchers for the new Centre for Enzyme Innovation at Portsmouth. The focus of the group remains the engineering of biological catalysis for the breakdown of a wide range of natural and synthetic polymers. The group recently joined the Bottle Consortium, which offers new opportunities for true interdisciplinary research across the diverse areas required to tackle the global plastic pollution crisis. Please welcome Professor John McGeehan.
Well, thank you very much for the invitation. Yeah, it's lovely to speak to the Winchester branch of the Café Scientifique. It's a great organization, and I think it's really super to see all these faces that are interested in listening to some science on a rainy Monday evening. So thank you for joining. I hope I can keep you entertained for the next 45 minutes or so. So what I want to speak to you today is about our current research, which is all about enzymes, and enzymes particularly that can break down plastic, which, as you know, is turned out to be rather a global problem. And I think, you know, we're all watching this on Zoom or YouTube at the moment. So we're all touching, sharing, looking at, and being connected by a huge amount of plastic. It's really been an incredible material to connect us globally. And I think during lockdown, we've all been able to really connect with people who wouldn't have otherwise been able to. So plastic, of course, has huge benefits. I wanted to start with something that's a little controversial maybe, and people ask me this all the time. Why can't we go back to glass milk bottles? Because we knew how to recycle those, and you know, there's very good methods there for doing that. Well, of course, the problem is one of energy, and when we're coming up with new solutions, we need to really consider this. Not just the amount of energy we can save now and tomorrow, but maybe in 10 years or 50 years. And if you look at, you know, swapping out petrol and, you know, promoting diesel and offering government subsidies to go, you know, down that route, you know, it's quite apparent that that wasn't the right thing to do. And we couldn't have imagined that the particulate materials from diesel fumes would have such a bad environmental and health impact. So again, there's a good reason where we thought we're doing something positive and actually we're doing something rather negative. So the similar sort of thing is for plastic and glass milk bottles. The thing about these, so normal plastic milk bottles nowadays tend to be made up of around 40% recycled content, which is really pretty good. And if they are adopted more widely and the recycling is more joined up, we can pretty much close the loop on that and get it close to 100. Now that has major advantages because one, it means we're reusing that plastic over and over again, but we're also massively reducing the transportation costs of milk across the whole supply chain due to simply the weight of glass. So when we consider that across the whole supply chain, actually plastic can potentially win out, but, and it's a big but, only if the plastic waste is collected and managed and looked after properly. And this is where we really fall down. And of course, you know, plastic has many uses, and you'll find it in pacemakers and plastic heart valves. And, you know, it's part of its robust nature, and the ability to mold it into just about any conceivable shape is actually one of its incredible benefits and one of the reasons it's become so ubiquitous. Of course, there's many images like this that you'll find on the web, and, you know, plastic in itself is often overused, and we need to really consider that these days when it's a useful thing for the environment to use plastic and when it is not. And of course, we've become rather addicted to this material, and it's going to be very difficult to wean ourselves off this material globally. And of course, this is another controversial one, plastic packaging. It's certainly overused, but we need to consider this again quite holistically. You know, if we don't wrap cucumbers, then they go off in days rather than weeks, and there's a huge amount of potential food wastage at stake here. Of course, then we need to consider, do we need to transport all the food around the world so that we have every type of fruit and veg available all the years of the year, all the months of the year, I should say? Or, you know, should we be taking produce from closer to home, which immediately reduces the amount of plastic packaging we need for transport? So again, these are all complicated problems. So it's not a black and white, it's very much gray in some areas. No more so than this beach in Mumbai. Now this beach was actually cleaned up, but of course the problem is not on the beach here. The problem is actually out here in the ocean. And, you know, this plastic will continue to wash up on the beach here. You can see the vast amount of plastic bottles and plastic bags here. So just to put things in context, we're going to go back to 1907, where the first sorts of plastics started to come on stream. So anyone with a Bakelite phone in their attic, these are worth quite a lot of money these days. And Bakelite was first introduced by Leo Baekeland in New York in 1900s. And, you know, this was really the start of a revolution. And this is the front cover of Life magazine in 1955. And I think, you know, I feel sorry for this small child here, you know, nowadays thinking, oh my goodness, I was involved in this magazine cover where, you know, celebrating, you know, unchaining yourself from the kitchen sink, never needing to do any washing up and dishes again, because basically you could use these new materials once and then throw them away. And you had this basically incredible supply of never-ending dishes that you could be completely disposable. And of course, now we know the problems with this and where most of that has actually ended up. And you'll see many of these graphs. This one is from the Ellen MacArthur Foundation, and this shows the amount of plastic production in millions of tons per year, starting from 1917 when plastics were just starting to be introduced. And you can see this pretty much exponential growth as we go to 2021. We're kind of off the top of the screen here, unfortunately. And I think, you know, even though we've had people like David Attenborough coming on and, you know, telling the world about the problems and the environmental consequences of plastic pollution, actually, it's not just increasing, but the rate of production is still increasing. And China is building huge numbers of plastic producing plants. And the oil and gas going into those plants is going to be absolutely incredible. They're looking at overall globally 20% of oil and gas reserves going into new plastics by 2050. And we just cannot let that happen. That's a ridiculous scenario when there's so much plastics that could be reused already on the surface of the earth. So I'll come back to that in a minute. But of course, this is a real problem, and we're seeing something like, and these are hard numbers to estimate, I should point that out, up to 12 million metric tons of plastic entering the ocean every year. And there's some worse estimates than that as well. This is an interesting diagram because it shows where all the plastic currently is, all the 8.3 billion tons of it that we've made. And this total amount, you can see in this part in green here, about 3/4 of that has been used once. And the vast majority of that has been discarded straight into landfills, dumps, or simply thrown away. And here lies the problem. If you look at what's been destroyed, that's mostly burnt. The amount that's recycled here of that single-use plastic is really, really quite tiny. And this stuff here in use is the plastic in things like pipes, underground pipes, roads, buildings, that sort of thing, which is still in use today. And of course, one of the reasons it's such a great material is it does last a long time. But our major problem is dealing with this single-use plastic that's used once, sometimes for minutes, and then thrown away without being recovered. If we have a way of recovering that, we can really change the game completely here. And of course, one of the major things we need to consider is how much this is worth to people. And the global plastics market, depends who you ask, is worth about $1 trillion, which is a big amount of money. There's lots of money to be made in this industry. The current production keeps going up. This is the last number I had, which was 320 million tons per year. This is a staggering amount of production. I mentioned about the consuming our oils production, but these numbers are startling. Globally, only 20% is recycled, 25% is burned, and 55% discarded. And these numbers are kind of very rough averages as well. If you go to Sweden and they say how much has been recycled, it looks very high. That's because they consider burning plastic and taking energy out of it as recycling. I don't, because it's not actually circular, it's not being reused, it's being used once. So better than going straight into the ocean, but not a huge amount better. Excuse me. There's lots of statistics out there, but I think if we take PET bottles, that's our fizzy drinks bottles and water bottles, anything, if you look in the little triangle with number 1 in it, that's PET. There's about 20,000 PET bottles made every second. And I've been speaking to people at PepsiCo and Coca-Cola and these sorts of places. And again, these numbers are going up, not down. And about, if we take those big companies like Coca-Cola, PepsiCo, Nestle, they account for most of the plastic bottles. There's lots of other companies too, but actually that's a massive opportunity, I think. And these companies are now really starting to think about how to recycle more efficiently. And we're very keen to work with them to help. We know how to turn a plastic bottle back into a plastic bottle, but we hardly ever do it. It's about, in the last numbers I had from America, were about 7% are turned back into new bottles. In other parts of the world, that's closer to 1% or less. And the reason is somewhat economic as well, and I'll come back to why that is. Of course, the major problem is that some of these plastics, PET included, tends to last for hundreds of years when it does get into the environment, and we're seeing the effects of that at the moment. It does get broken down by the action of waves and sunlight, but only into smaller and smaller pieces. You may have heard of microplastics. So this is not really breaking down chemically, it's just breaking down physically. And these plastic particles will then enter the food chain. And, there's many images out there. This is just one, there's some much more horrific. But, the questions to ask ourselves here is, should this plastic cotton bud exist? Could it have been made of wood or paper that could be recycled? Or actually, does it even need to exist at all? And a lot of our convenience materials, plastic is a key component of. And of course, the major issue here is that any plastic discarded off our coasts here ends up in the sea, which is then sucked into these massive transatlantic currents and ends up in these ocean gyres. And the major polluters in Southeast Asia, just because of the lack of infrastructure there, all that plastic is ending up in these ocean gyres as well, and then recirculating around the globe. And what we're seeing, this is a diver. Let's see if I can make this work. Let's see if we'll play. It's not playing. This is a snapshot of a diver, Richard Horner, swimming off the coast of Bali in the ones crystal clear waters that were there. And what you can see here is these fragments of plastic, bits of plastic bags, smaller fragments from water bottles, and wrappers of all different descriptions are now sort of circulating. So it's not so much a plastic island as these things are once described as, more kind of a plastic soup of this particulate matter that tends to collect in these huge ocean gyres. And actually, recently I was speaking to the company Ocean Cleanup. You may have heard of them. They're the people that made these giant booms to kind of tow behind a couple of ships and sort of scoop up the surface plastics and then bring it back to land. And they've got a couple of container fulls of this stuff currently sitting in the Netherlands. And interestingly, there's not any plastic bottles in that. So you may think the plastic bottle is the killing thing that always gets out there. Most of those sink in rivers before they get out to sea, and lots of them end up at the bottom of the sea. So what we're normally seeing in oceans is discarded fishing gear, sort of the harder plastic crates and bottles and drums and that sort of thing. So yeah, there's a real problem to address here. Now it will play, typically. So yes, you can see here as this diver is swimming through, it's literally this kind of plastic soup, and it's just inevitably it's getting caught up in the natural habitats of all the creatures that live there. So thinking about PET bottles and what happens to them currently, we need to kind of think of what we're doing in a kind of linear economy style, because we're digging up oil and gas. We're then distilling the products from that to make these monomers. So these are chemical building blocks that we then can zip up together to make these long chains to make plastic for things like single-use PET bottles. The problem is this is ending up in landfill and being downcycled and then ending up in the environment when it's leaking out there. So what do I mean by downcycling? Well, let's see if I can get it. Okay. What I mean by downcycling is that often when we do recycle, when you put those PET bottles in the green bin, they're often collected. Quite a lot of them in Portsmouth are actually incinerated, believe it or not, which is a tragedy. We're one of the worst recyclers in the country, so we've got a long way to go. So the bar is quite low for us. But in general, considering how developed our country is, and overall, it's ridiculous. And every single county you go into has got different recycling strategies, making it very difficult to connect things up, actually. But those bottles do get collected and they do get recycled, they end up going into materials of lower value. And that's because when you first make the polymer chains, they're very pristine. They're very long, actually, and they've got beautiful properties. What I mean by that is they're crystal clear transparent. So they're not yellow or gray. And also they're quite soft and pliable, so you can use them for lots of applications. After a few rounds of mechanical recycling, which you basically sort those PET bottles and melt them, inevitably you get some color leaking into there for the color bottles and labels and all sorts of contaminants. And what happens is the plastic starts to go a bit gray or a bit yellow, and it starts to become a bit less ductile. It becomes a bit more brittle. So you can only do that a couple of times, and then the value is going down and down each time. It's often turned into textiles, which require less material properties. So this jacket and this shirt, anytime you see the word polyester, it's just plastic, PET plastic normally. And then after that, those textiles are very rarely recycled. And if they are, they're downcycled again into carpets and things like this, which then are actually negative value. It costs to recycle those. There's no intrinsic value left. So what you can see here is, although we're putting those bottles in the green bin, they're not really being circularly recycled. They're just ending up on a downward trajectory towards landfill or incineration. And that's something we can change. And I believe it's something we can change. Okay, so let's take a quick look at what's happening here. This is a TED talk, a fragment from a TED talk by Emma Bryce, and it really nicely illustrates what's going on here. So we're doing something quite crazy, really. We're spending a huge amount of money, energy, and time digging fossil resources out of the ground. So these are just carbon products. We make these carbon-based molecules. This one's terephthalic acid and ethylene glycol. And we zip them up together with these ester bonds, which hold them together, and we make polyesters. And PET is one of these polyesters. We kind of make it into these pellets. We then melt it down to make these preforms, which we then convert into any shape of plastic that we like. These are plastic bottles. We fill them with our fizzy or still drink of choice. We then use them and throw them straight in the bin. And as I mentioned, much of that plastic is not well recycled, and that the stuff that is recycled very rarely is turned back into a plastic bottle. So that's a really silly situation. So if we think about plastic more generally, throwing plastic, we've literally put huge millions, billions of tons of plastic waste into the environment. And this is a rubbish experiment in many ways, because if you're going to design an experiment, you couldn't have designed this any worse. We've put about 200 common different types of plastic into every environment in the world. The sea, deep sea, polar caps, you'll find plastic bottles at the bottom of the Mariana Trench. And now we're trying to figure out what to do. And it's a really, really difficult problem. We've made this really challenging for ourselves. So that all sounds very negative, but there is a positive spin on this. This is Professor Simon Cragg, who's a marine zoologist who works in our team, a long-term colleague and friend. And he spends his time out in Papua New Guinea and various places out in Southeast Asia. This is one of our colleagues in Jakarta, in the mangroves. And the mangroves are really interesting environments because on the one hand, there's massive amounts of turnover of carbon there. Basically, nature doesn't waste anything. It recycles absolutely everything. And if you think of all the plant litter that falls into those mangroves and is turned over and reused every year, it's absolutely staggering. Same for rainforests, etc. But those mangroves with those big roots that act a bit like sieves, they unfortunately collect huge amounts of plastic waste. So that's a real problem for this area. But it's also an opportunity because this is exactly the type of place where you've got massive enzyme turnover, breakdown of natural polyesters and natural wood-like materials in combination with lots of man-made materials. This is where evolution is really taking place. So that's a big question. We put all this plastic in the environment, and nature has got an amazing ability to regenerate, but can it do it with the plastics? And that's really was an open question until 2016, when a Japanese group reported this incredible bacterium, which was found in a plastic recycling dump in Japan. And this bacterium here is called Ideonella sakaisiensis, named after the city in which it was found. And there was the group were scraping around in the soil and wastewater runoff from this recycling plant. And they found bacteria that weren't just living off the bits of sugar and organic material that was left on the fizzy drinks bottles. This stuff was eating the plastic itself. And that's incredible when you think about it. And this is kind of evolution in action. The selection pressure of, bacteria there, fighting over those small bits of sugar left on the bottles. If you're the bacterium that evolves the ability to eat plastic, suddenly you have an unlimited food source. And that's really what we think is happening here. And they were able to take this bacterium back to the lab and culture it, and it could actually use just plastic as a food, a carbon, and an energy source, and that's quite incredible. And the way it does that is it secretes a couple of enzymes, and that's what I want to talk to you about next. So what is an enzyme? Well, all an enzyme is a biological protein that acts a bit like a catalyst that speeds up reactions. And just as we're digesting our dinner here, we've got all those protease enzymes that are breaking apart the carbohydrates into sugars and the fats into different small molecules. Enzymes are ubiquitous in our bodies, but also in nature. And enzymes tend to either make things or break things. And we're really interested in the enzymes that break things. And we use enzymes that break things all the time, of course. Our powdered biological washing powders contain lots of enzymes. So your typical one contains about 5 or 6 different types of enzymes. And these help digest stains, they help condition the fabric and actually trim off the ends of the cellulose in your cotton jumpers, which makes them a bit smooth and less bubbly. So all these things are performed by enzymes that were originally found in nature and then brought back into the lab, made faster and more robust, and then used for industry. And industry uses them for lots of different things, cosmetics, detergents, I mentioned. I've been working with colleagues for several years on enzymes that can digest waste wood and turn it into bioethanol and other chemicals that currently you can only get by oil. So making sustainable green chemicals, textile industry, food industry. And this is really important because if you're going to come up with a solution to solve plastic pollution, you want something that's a mature technology that people really understand already and can operate at scale. So that's another reason why I'm quite excited about the potential for this. So here we are. This is our bacterium. So what happens? Well, it binds to the surface of the plastic, and then it starts to produce these enzymes. And what the enzymes do is they start to break down the plastic. Now, as I mentioned, currently what happens is we take oil and gas and we make monomers. These are the building blocks. And then we link them together in big long strings through the formation of a bond, a special bond, chemical bond called an ester bond. And that's why we have these polyesters. And what this enzyme is an esterase. It's an enzyme that snips those bonds apart again, like a big pair of molecular scissors, and gives us back the monomers. Now, that's actually really exciting because if you can get the monomers back, they're exactly the same as the ones you get from oil and gas. So you can turn off the taps there. You don't need any more oil and gas. We've got plenty of plastic up here on the surface that we can do this with. So this offers the opportunity for infinite recycling, in fact. So there's 2 enzymes that this bacterium produces. One is called petase, and the other one is called hetase. And these basically start breaking down the plastic. First of all, the petase binds to the surface and starts breaking down the long chains. And then the second enzyme comes along and starts breaking them down into smaller units. Eventually, TPA, terephthalic acid, and ethylene glycol, which is the stuff that's probably in your car radiator, or the stuff they spray on planes for de-icing. So this small molecule. So the idea here then is you take your plastic bottles, you still need to collect them. You then basically, in a big vat, you pour in the powdered petase enzymes. You break the plastic apart into a clear solution containing the monomers. You then purify those, and then you can sell them back to industry to make new polymers. And those polymers are crystal clear. They're as good as, in fact, sometimes even better than the monomers from oil and gas. And you can reuse them again and again and again. So this was pretty exciting. And when we started looking at the structure of this enzyme, it really captured the news headlines. This was CNN back in 2018. Where spinning enzyme pictures actually made global news.
An enzyme that just so happens to be really good at breaking down PET. Now that is a type of plastic used since the 1940s to manufacture millions upon millions of plastic.
So this was, of course, a team effort, but that 2018 paper reached an audience of 200 million people around the world which was a bit of a shock. It was certainly a shock for me. It was a shock for my inbox, which was broken for about several weeks. And but it's great that so many people were interested. It came out around about the same time as Blue Planet 2. So Sir David Attenborough did have a lot to do with the profile here, but also people were really looking for potential solutions. And we were able to really capitalize on this for funding, which is really, really important. I would say that, interestingly, the global interest has continued. And after that paper in 2018, our paper in 2020 reached an audience even bigger, about 10 times bigger, actually, 2.5 billion people. So that starts to become a reasonable percentage of the world's population has actually heard about plastic-eating enzymes, which is really astounding. And again, this really helps us when we're trying to get the message across to people of what kind of science we're doing. It also adds an immense responsibility to do something good with this knowledge. And I would say that both of those papers have about 20 authors on them. It's a real big research team effort, transcontinental as well. So in this particular study, from the UK, the US and Brazil. And we have to operate in these big teams because the science is quite difficult. So we really need experts from all around the world. So I'm basically one of the spokespeople for these teams. So how did we do this? Well, what we do is when we get hold of that bacteria from the Japanese recycling plant, we can actually pull out the DNA. That's quite easy nowadays, and find out which DNAs or codes are making the enzymes. We can then put those DNA codes in our lab strain of bacteria and make lots and lots of the enzyme. And what you see here is me making crystals of the enzyme. These are purified enzyme solutions that we can crystallize, just like salt crystal, a bit more fragile, but the same principle. And then we take them to these amazing facilities like this one. This is the Diamond Light Source in Oxfordshire, where we can shine really intense beams of X-rays at these crystals. And that allows us to see incredible details. So using like real state-of-the-art detection techniques, this is a custom detector from the Diamond Light Source. What you see here is a diagram of, this is our protein crystal. So this is our crystal of the PETase, the plastic digesting enzyme. We blast X-rays at it, and then these dots that you can see on this detector are the X-ray diffraction patterns. And if we collect enough of those, we can actually do something quite special, which is solve the three-dimensional structure of the enzyme. And I still remember when we first saw this on the screen, it was so exciting. You know, this is the real 3D structure of the enzyme that breaks apart PET plastic. And why do we go to all this massive effort to get these 3D structures? Well, because this is a template. Once we can see this, we can start to understand how it works. We can start to understand the intricacies of it. And more importantly, we can start to engineer it to be faster. These natural enzymes tend to be really slow. I mean, it's amazing they're doing this job at all. But for an industrial purpose, we need something that's much faster. So this is really what we're going for. So, you know, this exciting moment, you know, a few of us, there was a champagne pop at some point during that evening when we saw this. Because we knew this was really quite special. And of course, the first thing I did when we got this 3D structure is compared it to the database of 3D structure that's available for everyone to look at. The nice thing about this branch of science, it's very, very caring and sharing, and all the data is made public and is shared around the world. And to be honest, this is quite disappointing because the PETase enzyme in blue here is the one that digests PET. And this enzyme in green, called acutinase below, is one that we've known about for decades. And it pretty much looks exactly the same. You don't need to be a structural biologist to see how similar these things look. But this turned out to be really interesting. So what is acutinase? Well, it turns out if you look at the surface of plant leaves, just about all green plant leaves, if you run your broccoli under the tap, you'll see the same thing. The water kind of bobbles and runs off just like you've freshly waxed your car. And that's because there's a layer that protects these plants called cutin, and it's a natural polyester. This is a polyester that is waterproof and kind of protects from invasion from bacteria. Of course, bacteria have been evolving at the same time as all these protection mechanisms, and over millions of years have evolved enzymes to break through this polyester cutin and invade the plants and get into all that tasty, sugary cellulose inside. So what we think is happening here is actually, this is actually a close-up of the cutinase enzyme. This kind of valley here is where the chemistry takes place. It's called an active site. And this is where this enzyme called cutinase breaks apart these natural polyesters on the surface of leaves. If we then compare this active site to the one that eats plastic, what you can see is a few small changes in the DNA, and this cavity is opened up here. And now this enzyme, without very much change to the DNA, has evolved to eat plastic bottles. And I think that's really incredible. It's basically evolution in action. And I believe, and we're already seeing evidence of this, if we look hard enough in nature, Simon Cragg out there in the mangroves in Southeast Asia, we will find other bacteria that have evolved other enzymes to eat a whole range of different plastics. And I think this is a very exciting opportunity here that we have in front of us. It's learning from nature, and then it's taking that back to the lab to see if we can make it faster still. And we can. So can we make it faster? So here in yellow is a chemical diagram of PET. You can see these repeating units here, each one held together by an ester bond. And here is the protein, the enzyme in this active site. And we can see this is the molecular scissors here. These residues break this bond and literally break the chain into the monomers. So what we try to do is fiddle about with this active site, and we change the DNA code. And we actually decided, let's do an experiment and see if we can change it back to a plant-eating enzyme. So we changed the DNA back to what looked like a plant-eating enzyme. And lo and behold, it didn't eat plants, and it still ate PET. In fact, it ate PET about 20% faster, which shows you how little we understand about these enzymes, actually. So this was a real shock. But what we could see when we modeled this is that the reason for this is the PET, when we make these changes, can fit more snugly into that cavity. The distances between those molecular scissors are shorter and the enzyme's more efficient. And what we can see here is really, this is the electron microscope image of the plastic at high resolution before we add the enzymes. This is the natural enzyme after a couple of days, and this is our engineered enzyme after a bit longer. And what we can see here is that it's actually eating the plastic faster, which is really exciting, actually. Okay, so can we make it faster still? Yes, we can. So this is the latest enzyme that was published in 2020, and this is the second enzyme, MHETase. And when we solved the structure of this, it's about double the size, and we really wondered what this one was doing. But if there's any chemists in the audience, this is what we tried. So this graph here, if this is titrating in PETase along the top. So as we go from left to right, we're adding in more PETase. And we go from top to bottom, we're adding in more of the second enzyme that this bacterium produces. And as we get a darker color, we get more plastic breakdown. So here, when we've got no enzymes, we've got nothing happening. When we add more and more PETase, we can see we get to this point here, but no further. When we add in lots and lots of MHETase without the other enzyme, we see nothing at all. It really doesn't have an effect. But the key is, when you add them both together, you can see there's this synergistic relationship till we get to this point here, where we get like about 6 times faster enzyme breakdown at a ratio of 2 to 1. And that's really interesting, because if you go back to the original bacteria, it produces these enzymes, it secretes them in about the ratio of 2 to 1. So, if we'd looked at that in the first place, we could have probably figured this out a lot quicker. And it just shows you how much you can learn from nature. We then decided, okay, how about if we take these individual enzymes and try and link them together to make a super enzyme? And that's exactly what we did. We did this in the lab, and this is the structure of this enzyme, where we created this chimeric enzyme. And again, that was much faster still. So we can continue to do this kind of iterative approach of learning a bit from nature, making things faster and faster. And in this case, you can see going from these improved enzymes from left to right, you can see the speed of the plastic breakdown going faster and faster. So we're making good progress here. It's really quite exciting at the moment. So can we go faster still? Well, yes, because the team here is now working around the world in places like this. We've got collaborators out at Yellowstone National Park in these hot springs, looking at bacteria that are growing in these really hot environments. Because if we can get bacteria that can grow in hot environments, we can get really fast enzymes that work at higher temperatures. And particularly for plastics, when you heat them up to about 60 or 70 degrees, they start to become quite soft, and enzymes start to work much, much faster. So if you're looking for a kind of industrial process, you kind of want these sorts of enzymes. And we've got about 100 of these at the moment in the lab, and some of them are looking really quite exciting. Okay, so remember I showed this. Okay, this is that who cares moment. That's all very nice, John, but what are we going to do with these enzymes? So I showed this linear model of going from oil and gas production all the way to landfill. How can enzymes help? Well, the idea is pretty simple here. It's really transforming from this linear economy of digging stuff up, using it and throwing it away to something much more circular. And the idea here is if we use enzymes, we can take the plastic that we already have on the surface and just infinitely reuse it. By breaking this plastic down to monomers, we get material that's as good as the virgin stuff from oil and gas, but it's even better because it saves a huge amount of energy and a huge amount of greenhouse gases. And any company that use it can say that they're using recycled material, which there's of course a huge appetite for. There's lots of reasons why this is a good idea, but the main one is really one of environmental benefits. It could make a real step change. The key here is cost, and that's the first thing industry always asks, how much is this going to cost? Actually, when we first published this study, the first thing industry didn't ask, it was something different. It was a big recycling company, I won't tell you which one. And they said, yes, the first thing we did when we saw your story in the paper was do a full risk analysis of your technologies to our business model, which was a bit of a surprise. But then thinking about it, they've invested billions in new plants, recycling plants, and they've got supply chains that are very long in the tooth with very tight profit margins at each stage. So we need to come up with something really quite transformational and cost effective for them to uptake this, and that's what we're trying to do. Our latest study, which will be published in a couple of weeks, open access, available to everyone, will show that this technology, particularly for PET, can be cost competitive, but also with huge environmental benefits. So we're at the Centre for Enzyme Innovation. We're very lucky. The Research England, the government body, funded us to the tune of about £6 million. And we have a team of people here, it's kind of PIs in our team, lots of different scientific areas together. And we're able to go out and hire 15 researchers in specialist areas from all over the world to come and join us. And this has just been fantastic. So there's now about 30 of us, PhD students and senior professors all the way through. And it's just been such an exciting place to work. But, there's still a way to go here. How can we make these things at scale? And I mentioned, maybe a negative thing about a company here is a positive one. GlaxoSmithKline, who have a major manufacturing plant in Worthing. In fact, most of the world's penicillin is made there, that I didn't realize was made there, invited us to come along and have a discussion. And they said, okay, we happen to have the world's crack team of fermentation specialists for upscaling enzymes for GSK Global based in Worthing. Can we help? I'm like, yep, I think you can, but I don't think we can afford it. And they said, oh, no, actually, as part of our corporate sustainability, we were happy to do this, and they started making enzymes for us at scale. This is a really interesting time when companies want to work in environmentally green areas, and we can really benefit from that. So not only do we have some of their facilities at our disposal, but we've got their expert team to help us too. So this is a bit of an unexpected positive and step change. But of course, that's one type of plastic. We have got lots of other types of plastic that we need to deal with: polyethylene, plastic bags, polypropylene, so the harder plastics, polystyrene, those annoying takeaway trays. And we need different enzymes for different plastics. So we're really trying to upscale things. And one of the ways of doing that is to really start to work in collaboration. So the idea here is to kind of go around in these big circles. We take all the consumer waste and add enzymes, make them at scale, try and collect as much plastic as possible, get it out of landfills and back into recycling plants, and then try and make value out of it. So here's an idea that one of my colleagues is working on. You take those monomers, those building blocks from PET, you add a few extra ones to it, and you make fiberglass. That's worth 10 times more than the PET, because you can make wind turbine blades out of it, or you make Kevlar, you make carbon fiber. So these are materials that the automotive and aerospace industry are crying out for. If you can make those from waste material, the idea is that you turn that waste and make it valuable. And that is where there'll be a switch, I believe, towards recycling and at scale. So that's really where we need to get to. And I'm pretty positive we can do that. The appetite is huge. Governments are turning their attention to this. We'll see what happens at COP26 in Glasgow this year, and how willing nations are to get together and really push forward. The change in administration in the US is very positive for the environment. Let's see what actually happens, as opposed to what politicians just say might happen. But there is a big push here, and I think we can take advantage of that, not just for the science, but also pushing policy and making companies, recycle more and make them more responsible for the plastics they produce. And they want to be, and they really want to try. We just need to deliver cheap technologies, and that's what we're trying hard to do. So as I mentioned, speaking on behalf of a big team of people here across the globe, we're based at the University of Portsmouth, but we work really globally. And I think that's the way forward. It's not to be competitive, but really to start to work in big consortiums like the Bottle Consortium, bottle.org, if you're interested. These are going to be the game-changing things where we bring lots of scientists together for a common problem. So thank you for listening. That's quite a long talk. I hope that was okay. Let me stop sharing my screen and I'll pass over to William again.
Well, if everyone would please mute the microphones, and we'll start working our way through the questions that we've got in the chat. Christine's saying another approach is to replace oil-based polymers with natural polymers. I guess there are limitations to what they necessarily do. Is that something you have sort of much of a thought on, John, or is that sort of outside the frame of what we're covering?
We work with colleagues. I mean, I think one of the, so we're building new labs at the moment where we can start making polymers. And that sounds like the opposite thing we should be doing, right? But actually, what we want to be able to do is complete the circle so that we digest plastics down to their building blocks, and then we remake them to test their properties. And we do that over and over again so that we can really understand the whole circle. And we're working with, there's a company in Southampton, actually, Bioplastics, that are developing a whole range of bio-based plastics. We hope to work with companies like that, where while they produce new types of plastics, we develop parallel recycling streams. We need to be careful when we develop lots of new plastics, that it would be better in some ways to simplify the number of plastics and reduce the different types of plastic that we need or use, I should say. But it's all about, you mentioned material properties, that's absolutely key. And people want things that are lighter weight and stronger. So there's a lot of plastic development going on. One of the things that people are looking at, which I think is quite exciting, is you make these long polymer chains as before, but you put little Trojan bonds in there. These are bonds that you can access at the end of life through maybe a light treatment or a particular chemical, which then allow you to recycle them. So they maintain their specialist properties over the lifetime, but we actually have a method to break them down in the future. We didn't think about that 100 years ago, unfortunately. If we had done, we might have been in a better place now, but certainly we have the technologies to think about that now. Yeah.
So will the plastics of the future be produced by biologists rather than chemists?
Maybe. I think as with many of these things, it will be a combination. We'll be needing the biologists, the chemists, but also the chemical engineers, the people who understand the material properties and what to do with them. So it's getting all those people in the same room. Science traditionally works in little niche areas, but now it's very much moving forward to getting everyone speaking together on the same level.
Okay, a question from Simon on YouTube saying, fantastic talk. How easy is it to separate the enzymes from the pristine new polymer? I suppose you mean pristine new monomers, strictly speaking.
Yeah, so that's a great question. Enzymes break down naturally in the environment, so we're not worried about safety concerns. They're non-living, but you're right, from an industrial standpoint, you want to be able to reuse them. So there's a couple of ways you can do this. And again, this is the good thing, we can borrow technology from other well-developed fields. You can, for example, you can attach the enzymes to little magnetic beads. So at the end of the process, you can just put a magnet on the side and draw them out, and then for the next batch. You can immobilize them, sometimes in kind of meshes and networks and things like that. That's also been done quite a lot. But to be honest, those are completely untested technologies at the moment, and we need to develop them. But you're right, in order to make a cost-effective process, we can't just throw the enzymes away. We want to be able to make them robust and reusable over and over. Of course, in some ways, that's what we do with biological washing powders. So we just pour it away. If we can make them that cheap, that would be great. But ideally, we'd want to try and reuse them where we can.
How generic is the esterase that you're working with? I mean, would it work on terephthalate in fibers, in sort of clothing fibers, for example? Or, I mean, I guess ideally you'd want to fine tune some things for a specific polymer, but is there enough sort of flexibility within the enzyme, or would they just not work?
It's a great question, and we can tune the enzyme for those different materials. Actually, if it's got an ester bond, then yes, we can break it. Often the question is how quickly, and actually fibers are actually the way they're made and extruded. They're quite highly crystalline, which gives them an extra added strength, but actually an extra problem when you have to break them down with enzymes. So we're looking at kind of processes because it's very similar to the problem actually of breaking down cellulose to make bioethanol. It's like long fibers that you need to break apart. But textiles are much bigger, like, polyester textiles are a much bigger volume, quantity, weight, whatever you want to, unit you want to use compared to plastic bottles. It's just that plastic bottles are kind of the show child of plastic pollution. But actually textiles are much worse. There's massive warehouses full of the stuff, and a huge amount just goes to landfill and incineration. So we are looking at doing this for textiles as well, for sure. And actually, again, to come back to your question, we can use cocktails of enzymes. We've already got enzymes that can break down cellulose and cotton. So you can imagine, most textiles are mixed, all waste is mixed. So we need to think about that quite carefully. By using cocktails of enzymes, we can break down the cellulose and cotton into sugars, and then the plastic into monomers. And we've got the separations technology, ironically enough, from the oil industry, and we can employ that to help us.
Some of the older members of the audience might be familiar with the New Scientist cartoon from the 70s of Grimbledon Down, where they were constantly trying to find new ways of making new foods chemically. It sort of has slight echoes of that.
Yes, it's
Um,
funny. There's hidden truths in some of these things.
yeah. Ken's asked, can the PET and MHET enzymes be run at highest temperatures? I assume he's sort of talking about, you mentioned running them at about 60 or 70, but I suppose he's perhaps asking about the potential for running them at higher temperatures still. Would that be fair, Ken? And you're on mute.
Yes, it would be. I know they tend to fly apart, these big molecules, don't they, at higher temperatures? And I mean, there is precedent saying things like the brewing industry, they run at sort of 160, 170 Fahrenheit. So can you do something similar?
Exactly what we're doing right now. Actually, we have bioreactors running as we speak at 70 degrees in the lab with enzymes that we have found in hydrothermal vents, hot springs, and kind of extreme environments around the world. And they do. I mean, some of these bacteria live at 100 degrees centigrade, and the enzymes that they produce are incredibly robust. The ones that I spoke about in my talk from the plastic recycling dump, the PETs and METs, they stop working about 40 degrees. They've been evolved to work at kind of ambient temperatures. But of course, we can take the thermotolerant versions from these extreme bacteria and use those, and we're seeing amazing results from those. That is speeding things up, not just several fold, but tenfold. So I think this is really what we'll be looking to do, is develop technologies that work about 60 or 70 degrees with enzymes that can tolerate those temperatures.
What sort of scale of plant do you envisage this using? I mean, is it going to require something on the scale of where the UK would only have one plant for a viable thing, or are you looking at something where a fairly small island in the Pacific could have a viable plant themselves without causing too much intrusion to their environment?
Yeah, I mean, we're hoping for the latter. There's a 50,000 ton per year demonstration plant currently being built in near Lyon in France. So, there is investment going into building these plants, and we'll be watching this very carefully to see how they get on.
And that's specifically using your technology for that sort of volume?
It's using a slight variation. They used a slightly different enzyme, but it is a polyester breaking enzyme, which they've patented and they're using in that process. So that's really exciting. Actually, it means that we've got to that stage already to actually, build plants and get concrete in the ground. What we'll be speaking to recycling companies, and if you speak to them, often they'll say, look, just give us a big shiny box where we can put our waste plastic in that we currently can't get any value out of, and make some value out of it. We don't care if there's enzymes in the box. And actually, this is a wake-up call for us. The world doesn't want enzymes. The recycling industry doesn't want enzymes. But they potentially want enzyme-based solutions. So we need to have a solution that, like, you build a bioreactor this size, drop it into your plant, you can put your PET waste, and you'll make this much money. So we've started talking to chemical engineers and engineers that can build these sorts of plants at scale to really try and understand what we need. We need to absolutely make sure that the enzymes we develop in the lab don't just work in the lab, but they're actually designed to work in these industrial scales. But I think they don't necessarily need to be huge. These are things you could retrofit current recycling plants with.
Milan has asked, saying that you mentioned converting waste wood into ethylene to use as fuel. Does this lead on to any way of short-circuiting the problem of the day and converting waste plastics into hydrogen using enzymes?
People are trying this, actually. They've not managed it successfully at any sort of sensible scale. But the fact is that plastic contains a huge amount of energy. You only need to burn some plastic and you see how much energy is released. It's an incredible resource that, burying it is just insane, really. When we can recover those things, there's all sorts of technologies that we can extract that energy to make. Making hydrogen, that's going to be tough, but I wouldn't necessarily rule it out. There's many competing technologies at the moment, thinking about fuels for the future. Hydrogen has its issues, and the cost and availability of how to use that in a kind of dispersed infrastructure is going to be hard. But we can solve these things for sure if there's a big enough appetite.
And what prospects do you think for a solution to the polystyrene problem? That seems to be one of the most intractable ones in current systems. Yeah,
polystyrene is quite tough. You can chemically break it down, but that uses pretty toxic chemicals, or you can pyrolyze it, which involves really hot reactors, high temperatures, high pressures, that sort of thing, which isn't very ideal either. That costs a lot of money, which makes it expensive and less attractive to do. There are some hints of enzymes out there from organisms that can break down polystyrene and other similar types of plastics. We need to really make sure that that's really what's happening, and we are looking at some of those enzymes now to see how they operate and if that's actually true. But again, that is something that if we could get enzymes to break them down into their building blocks, that could be a really attractive low energy solution.
Interesting. And when talking about the wild bacteria that were found in the plastic recycling plant, what does the bacterium gain out of the breakdown? Do they just get enough energy that they can transfer from splitting the ester bond, or do they then feed on one of the substrates?
Yes, well, that was one of our questions as well. And what's quite interesting, these bacterium is probably the reason why they can do this, is they have evolved transporters on their surface that they can actually ingest terephthalic acid and ethylene glycol, and then that goes into their central metabolism, and they actually break it down and make more molecules out of it. So literally that carbon is coming into the bacteria, and they're breaking those bonds as an energy and carbon source. So yeah, it's really quite incredible. I think probably they're doing it when they run out of food, because obviously sugars and other sorts of things they'll take in preference. But they have got this incredible ability to switch over to eating plastic when the sugar runs out.
Okay, so the wild bacteria are not actually terribly useful for producing reusable monomer materials, because they want to eat it. But if you isolate the enzyme itself, then you don't have to worry about feeding that.
Well, there's two schools of thought there. So the simple way is, we're starting with the simple one, which is to make really good enzymes and just use powdered enzymes to break down, reuse the monomers. But there are actually a number of really interesting industrial strains of bacteria, particularly Pseudomonas bacteria, where they've already engineered pathways that can take any substrate. As long as you can grow these things, the pathways have been designed to produce certain bio-based chemicals, which are very valuable. Vanillin, for example, you can produce with bacteria. It's very expensive to get it from the plant, so from the natural sources, I should say. So you can make it in bacteria by using these sorts of things. So you could imagine that could be valuable too, because then you could just have bacteria growing and producing the chemical of choice from that waste plastic. Quite a long way to get to that point, though, I would say.
And is the process that you've developed endothermic or exothermic, or sort of neither one nor the other particularly?
So it's a mixture. When you break the bonds, you release energy, but then when you transport them and you take them in and start putting stuff together again, it's going the other way around. So you have these pretty complicated energy cycles throughout the process. That is something that we need to take into account. The other related thing to that is when you break apart polyethylene terephthalate, one of the monomers there, the building blocks, is terephthalic acid. So you're making an acid. So if you don't take care of that, the acid will eventually drop the pH and kill the enzyme. So you need to add base in there, and that has a monetary cost. So again, you need to look after the chemistry and the thermodynamics. So it's quite interesting. It really does involve biology, but also chemistry and physics as well.
Yeah, it's fascinating. I guess most things, the traditional silos just don't really make much sense anymore because everybody's having to work collaboratively. And I suppose when you're training undergraduates, they've got to start somewhere, and having one block of skills is a good starting point. But as people progress through their careers, if they stay in STEM, then they are going to be working across any sort of arbitrary boundaries in disciplines anyway.
Yeah, I think that's very much the case. I started off in microbiology up in Glasgow, and then I did structural biology over in Grenoble in France, and I never ever thought I'd be working on plastics. So it's great. I do very much enjoy the cross-disciplinary nature of the work, and the students love it as well, mainly because they can travel around the world, or they used to be able to. Hopefully they will again soon.
Yeah. Simon again on YouTube's asking, can you see us mining landfill sites in the future for the plastics? Is that going to become our source of feedstocks?
That would be great, wouldn't it? I think, a lot of the easy stuff has already been taken out. So the polyethylene terephthalate, the plastic bottles tend to be extracted quite efficiently these days. Well, certainly in the UK, not around the world. But yes, if we can start having enzymes that digest the other common plastics, polyethylene, for example, polypropylene, and that's going to be hard. Those are carbon-carbon bonds. They don't have an oxygen in the middle, so they're much harder to break apart energetically, coming back to that question. So we need even better enzymes or different types of chemicals and different types of chemistries to break those. But that would be a dream if that could start happening, start reducing those landfill tips down and reusing them again.
I imagine polyethylene, polypropylene probably more challenging than polystyrene by the sound of things.
Agreed. Yes.
Yeah, so that's perhaps quite a long shot. And Bob's saying, how soon do you think it will be before we see this happening on a large industrial scale? And you talked about the site in Lyon as a pilot one, so presumably a full industrial plant could be very much larger than that at a European level or something like that.
Yeah, I mean, there is interest. Some of the big companies have expressed interest in getting together to co-fund those sorts of things. And I think that's quite exciting because that's the kind of capital you need when you're thinking about those big plants. It's well beyond anything we could do at the university. We need investors and a lot of business acumen to make these things work. But at the same time, we really need to address the problem quite urgently. I think governments realize this now, and I think many industries realize this now as well. And there are a lot of opportunities to make money in this space, let's not forget. So I think when we get the technology a bit cheaper, it will start to be taken up. As I say, the paper that's going to be out from our group in collaboration with our American colleagues in a couple of weeks shows that we're now at the point, I would possibly, maybe it's wrong to call it a tipping point, but certainly we're at cost competitive prices at scale. These are models, of course, we need to see what happens in practice, but we're hoping to have some plants starting to be built in the next couple of years, which is pretty exciting.
That's great. And before anybody leaves too depressed after what you were saying about Portsmouth and their recycling, I actually had a presentation sent through from a councillor in Winchester who was saying that all of Winchester's plastic recycling goes off to Veolia's recycling plant in Dagenham, and it then goes on for onward processing into various different things, whether it's new plastic bottles or textiles or whatever, and it's all within the UK. So that's quite encouraging stuff. Well, that brings us to the end of the formal meeting. Many thanks to John for an absolutely fascinating talk, and one I think that gives us a lot of hope for the future, and look forward to hearing when there are any more developments. And
Can I say, I thought that was tremendous, tremendously inspiring talk, John. So thank you very much.
Thank you all for listening. I really appreciate it. I mean, and thank you for some great insightful questions as well. Dawn had a question earlier, and I'm just going to share my screen very quickly, if I may. I don't know if you can see my screen. It's a Guardian story. Can you see that?
Yes, yes.
Yeah.
Yes.
So this was at the weekend, actually, or Friday it was. And it's not elephants, but it's cows. And yes, they're looking at the guts of cows as a potential place for finding bacteria that can break down plastic. So there you go. There's lots of potential out there that we're still untapped. So yes, I think there's a lot of positivity there. If we keep looking, we will find more of these things. So yes, thank you again, everyone. Yeah, at some point, hope to meet some of you in person.
Yes, we look forward to that.
Very much.
And thanks again.
Thanks, John. Thank you.
Thank you.
We look forward to seeing you all next month on the 2nd of August.
Thanks so much.